In the first two lectures, we tackle limits of a sequence and functions. So let us recall all of them. So first we have a limit of a sequence. So for a limit of a sequence, we have the notation so we read this as limit of uk. uk is what we call the term of a sequence. So the limit of uk as n approaches to infinity equals L. So L is the value wherein the sequence gets going to as the number of terms gets large. Now, if a sequence has a limit, a finite limit, so we say that the sequence converges to a given value. So we write it here. So the notation for a sequence, we have uk for the term, and we close it by open and close brace. So we say that this sequence converges if and only if limit uk k approaches to infinity equals L, which is finite. And then we say that uk diverges if and only if the limit of uk be either of the following. So does not exist, so DNE, or infinity. So if the answer is infinity, so this infinity here is different from this. So if I write L less than infinity, it means that L is finite, while this infinity, as k goes to infinity, so the terms of the sequence gets larger and larger. So this infinity here and this infinity here are different. Okay, so in getting the limit of a given sequence, I introduced to you the theorem called squeeze theorem. So the squeeze theorem means that if you have these three sequences, in such a way that the terms in the first sequence is less than or equal to the term to the second sequence, and then less than or equal to the term in the third sequence. So for n element of z plus, now if we take the limit of this term and the limit of this term, and they are the same, so let us write it here. So let us have L. Then we can say that the limit of Bn as n approaches to infinity must also equal to the value L. Okay, so let's have a limit of a function. Suppose we have a sequence, and in such a way, so each term of the sequence approaches to a certain value x naught. So then if we input each term of the sequence to the function, so the function tends to L. Now this L is what you call the limit of the function. So meaning for each term there is a corresponding function, and then so each function approaching to a certain value L. Now this L is what you call the limit of the function. Okay, we also tackle the so-called Lhopitals Rule, which says for given function f and g, if the limit of f of x as x approaches a equal to the limit of g of x as x approaches a, so if this is equal to 0, or the limit of f of x approaches a equal to the limit of g of x approaches a equal to infinity, if we take the limit of the ratio of f and g as x approaches a, this is the same as taking the limit as x approaches to a of the derivative of f divided by the derivative of g. So this rule helps us to evaluate complicated limits. Okay, so we can now continue our discussion by discussing continuous functions. So here's the definition of a continuous function. So we have here, so a function f of x is said to be continuous at the point x naught if we have this expression. So if we take the limit of f of x as x approaches x naught equals f of x naught. So it says here that if the limit of f of x as x approaches x naught exists and it is equal to f of x naught, we can say that the function f is continuous at the point x naught. Now, the function is said to be continuous if it is continuous at all points of its domain. So we have two meanings of continuous. So continuous at a point x naught and continuous at a certain domain. So let us take this example. So we are instructed to determine where the following functions are continuous. Okay, so let us do letter A. So the function is absolute value of x. Now, we know that the absolute value of x has a definition. So we have x for x greater than 0, 0 for x equal to 0, and minus x for x less than 0. So here we need to determine at what point or points where the function, the absolute value of x, is continuous. So we will use two-sided limits to determine where the function is continuous. To further analyze the function, let us graph it. So we have, so this is x and y, which is f of x. So our function looks like this. So this is f of x equal to absolute value of x. Observe that as x approaches 0, coming to the left, so let's have x minus, so here's 0. So if we take values of x coming from the left at 0, coming from the left of 0, we write it as limit x approaches to 0 minus of f of x. All values are negative, so we have minus x. Now if we get values of x coming from the right of 0, so we write it as limit f of x, x approaches 0 plus, all values are positive. Now, recall our knowledge in evaluating two-sided limits or evaluating a piecewise defined function. So in order for us to get the limit of f as x approaches to a, so we need to have the limit of f coming from the left of a as x approaches to the left of a, and the limit of f of x as x approaches to the right of a. And if they are equal, we can say that the limit of f of x as x approaches of a exists, and it is equal to L. Well, let's say this value is L, so they are equal. Now let's look f of 0. By definition, f of 0 is 0. And if we take the limit of f of x as x approaches 0, so it has two values. You have minus x and x, so which is equal to 0. So they are equal. Now, applying the definition for continuous, so the limit of f of x as x approaches 0 is equal to f of 0. So it satisfies the definition of continuous at the point x0. So by that, we can conclude that f of x, which is equal to absolute value of x, is continuous at x is equal to 0. So for continuity at a certain domain, as we can see in the graph, there's no gaps or holes in the graph of f. So by this, we can conclude that f is continuous on every values of x within this domain. Okay, so for the second example, we are given g of x, a piecewise defined function. So here's the graph of g. So as we can see, this is the red part is the graph g of x equals minus 2x minus 6, and this dotted point here corresponds to the graph g of x equal to 2, and finally this violet line here corresponds to the graph of g of x equal to x squared plus 2x minus 3 all over x minus 1. So as we can see in the graph, there are two holes here. So this is the first hole and this is the second hole. For this point here, although this graph has a hole, -1 is defined at this point. So based on the piecewise defined function, you are given g of x equal to minus 2x minus 6 for x greater than minus 1, 2 for x equal to minus 1, and x squared plus 2x minus 3 all over x minus 1 as x greater than minus 1. So we also see that the third function here is not defined at x equal to 1. That's why there's a hole in the line, in the violet line here. So this line here is not defined at x is equal to 1. So we can say that g of x is continuous at every point except x equals 1. There's something I forgot here I forgot to test if the function is continuous at x is equal to -1. As we can see in the figure, the graph disconnect at x equal to -1. Although it is defined at -1, but it jumps down. Let us check if the function is continuous at x equal to -1. So to do that, let us take the limit of g of x as x approaches to -1, so to the left of -1. So as we can see in the function, so at x approaching -1 coming from the left, so we have the function minus 2x minus 6. So here we need to take the limit of this function as x approaches to -1. So the value here is minus 2 times minus 1 minus 6. So we have 2 minus 6, we have minus 4. On the other hand, so we have limit g of x, x approaches to -1 plus. So meaning we need to get the limit of g of x as x goes to -1 coming from the right. So here we have the function x squared plus 2x minus 3 all over x minus 1, so which is equal to x plus 3. Now taking the limit of x plus 3 as x approaches to -1, so we see that we have minus 1 plus 3, we have 2. So we can conclude that the limit of g of x as x approaches to -1 coming from the left is not equal to the limit of g of x as x approaches to -1 coming from the right. So we can conclude that g of x is continuous at every point except x equal to 1 and x equal to -1.